Alright, friends and neighbors, time now for another OSPF networking video. This time we are going to talk about OSPF messaging. Now here is an OSPF message exchange. This is between two routers that are actually OSPF neighbors. And so they're talking right back and forth to each other. And you can see the two IP addresses that we're worried about are 192.168.2.253 and 2.254. Now as a little foreshadowing, I have the type of OSPF messages that we're going to come across today, and these are all defined in RFC 2328 OSPF version 2. Now we take a look at this, we can see that this conversation starts off with OSPF hello messages, and then we drop into something called database description messages, and then we've got link state messaging, LS messaging, and that goes back and forth a little bit, and then we eventually settle out back to hello messages. And that is what we're going to try and work our way through. Alright, so I will start with this. Protocol information packets, or all of the messaging that we talk about when we talk about OSPF, they all share one basic header. So there's really three flavors of message that we're going to deal with. One is the hello, one is the database description messages, and then things associated with link state messages. But we'll see that link state messages have several different kinds of message. And every message that we're going to come across has a basic header. And so these are the fields that are part of the standard OSPF header. And then depending on the type of message that we have, everything else after that changes. And we'll see that here in a minute. Now, OSPF link state updates are sent along what we call adjacencies. And I'm going to say that now, but we want to remember the difference between neighbors and adjacencies. And we'll talk a little bit more about that here in a minute. So I think it's helpful when we're looking at all of these messages to sort of understand why the messages are being exchanged and not simply try to memorize all the different kinds of messages. So OSPF has a couple of processes within the protocol. And so one of them is called the hello protocol. So that's sort of a sub-process within OSPF. And the whole point of the hello message is not only to say, hey, I'm here, but also to establish and maintain what we call the neighbor relationship. And so all OSPF routers come up and they say, hello, 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 is there another OSPF router out there? And if there is, that router will answer up with another OSPF hello. And then they say, hey, listen, so you're doing OSPF, I want to do some OSPF. And so that may start an additional conversation. So it also ensures that the conversation between the two neighbors is bidirectional. And by that I mean that if we're going to send OSPF information that way, we also want to send OSPF information the other way as well. And then hello messages are periodically sent out all active OSPF interfaces, and the absence of an OSPF hello message indicates that there's a problem. So as part of this, the hello protocol helps us elect what's called a designated router. Now, a designated router has the responsibility of maintaining all the link state information for that particular network. And the designated router is going to be somebody other than all of the other routers. And what do I mean by that? Well, if it's just two routers talking to each other, then one of them is going to be the designated router and one's going to be the backup designated router, and they'll communicate with each other. And they will communicate with each other and share link state information because they've decided to establish an adjacency. And that's a keyword and tricky phrase. But if there's lots of routers connected to a particular network, you can have lots and lots of them, especially in the backbone areas, places where you want redundancy. In that case, not all of the routers will be adjacent. They might all be neighbors. They might all share an interface on the same network, but they won't be in charge of the routing information, and so they won't be the ones that are offering the link state updates to everybody. And so that would be the designated router. So that's kind of the reason we do that election. So for this hello protocol, we need a hello message, and the hello messages are type 1. And this is what a hello message looks like. We can see at the beginning here, all of this first part is that general header that all OSPF messages share. And then this is the stuff that's specific to this particular router. So we can see who sent this to us, or who the designated router was, how often these messages are going to come out, and then the router priority. Well, let's talk about another process within OSPF, and that is synchronization. So we have to remember the difference between neighbors and adjacency. All OSPF routers that share the same network are neighbors. They don't all establish an adjacency. So when we want to make sure everybody's got the latest and greatest updates to their routing tables, that's the process of synchronization. And so it's important to be synchronized. Well, how do we get synchronized? Well, we're going to use another message type here to handle that. So only adjacent routers are going to be synchronized. And so these are routers that have agreed to share routing information. And certainly this is going to be our designated router. So the designated router is going to have all the latest and greatest information with regard to the link state messaging in the topology. Now, in order to understand whether or not you are synchronized, what routers do is they swap database description messages. So in order to be synchronized, we are going to add a couple of message types. So we're going to add a database description message, which is a type 2, and then a link state request, which is a type 3. And the reason that we need the link state request is because if we're not synchronized, we want to get the latest and greatest information, and we use a request to do that. So in the case of the database exchange, one router is in charge. And so what's going to happen is we'll see that a database exchange or a database description message goes one way, and it has an ID associated with it. The neighboring router will respond with an ID that matches the request. Now, it can also go the other way. So we send database description messages from the in-charge router, the other one answers. But then we might come right back and say, now I want information, and then I'll send an update back, again with a different set of IDs. Now, there may be many of these messages in order to get the database fully synchronized. And so there's a little flag that we set, the more messages flag. So essentially what's going on here is that we swap a database description message and we say, hey, listen, I want you to tell me your latest and greatest information with regard to your link state database. And so this is the information that comes back in the response to the database description polling message. After we bat this back and forth, eventually the routers become synchronized and have established a full adjacency. And again, the designated router is adjacent to everybody else, but everybody else is not necessarily adjacent to the designated router. And here is an example of the database exchange between our two neighboring routers. So we've got, in this case, it's a different capture. It's 1.253 and 1.254. And we can see that I closed off the basic header here. So this is a type 2 message. Both of these are type 2s. And we see that this is a database description message, and we see a couple things. One is that this is the in-charge router. This one is not, so the polling went from 1.253 directly to 1.254. We can also see that the sequence number in the two of these is the same, so they go together. And so what has happened is our in-charge router said, hey, listen, tell me what you got, and the responding router comes back with its link state advertisements. So a little foreshadowing, we have link state requests, we have advertisements, and then we have acknowledgments. These database description messages are the early stage of that, where we say, well, listen, tell me what your latest and greatest information is. Okay, here it is. And so this is the poll from this side, and then this is the answer from the other side. Now 1.254 might poll 1.253 in the exact same way. It would just be a different ID in the exchange. Okay, so let's talk about link state messaging. So far we've hit hello, database description. Now we've got link state requests. And what will happen is in the course of the database description, we may find out that somebody's got more up-to-date information than we do. And so we're going to make a link state request, and that will be forwarded to our neighboring router. And so what you're going to ask for is the link state advertisements that you think you needed updated, and this was established during the database description message exchange. Now you're going to get those. You're going to get the link state advertisements, which are type 4, but I skipped those for a sec because we're going to do the two easy ones. So you get the link state advertisements that you wanted, and you get a link state acknowledgement. Now you can do a very specific packet. Thank you. Here's my link state acknowledgement. Or you can use a link state update to accomplish the same sort of acknowledgement. So there's a couple of ways to go about this. We can also do it on a timing basis, or we can send it directly back to the sender right after it happens. Okay, so that's hello, database description, link state request, and link state acknowledgement. And I should do it like, let's see if I can do it that way. Now we got to do link state updates. So link state updates or link state advertisements, it's a type 4, but there are 5 different subtypes within the link state advertisements. So there are a couple of different LSAs. I've got them listed down here. So a type 1 is a router LSA. So this is about a particular router or routers. And then this is a type 2 is about the list of connectivity or the connectivity that a particular router has. Now the most common types of LSA are the router type 1 and the network type 2. These other ones are for larger or more complex topologies, or when we're communicating with routers outside of our area. But you will always see 1s and 2s, sometimes 3s and 4s. 5s are less common. Now these are also the types that are part of RFC 2328. There are other LSA types that I'm not going to talk about today that are not part of 2328. Here's an example of a link state update, and link state updates can also be compound packets, meaning that there's more than one LSA in a particular packet. So here's that basic header, and then we've got, this is a link state update. So it's a type 4, but a subtype of, this is a router LSA, so a type 1. Now, this is all about a particular router's state, and so that's the information that we have in this particular update. But if we take a look at a capture that I have, we can pull a link state update like this one, and I'll collapse some of the headers first. We can see first of all that this is a link state update or a link state advertisement. So this is obviously a type 4. So here are our LSAs, and there are 2 LSAs in this particular message. One is a network, right? Network LSA, and the other one is the router LSA. And we can see that in this particular case, this router was connected to several networks, or understood several networks in its link state database. And here we've got information about the connectivity that this particular router has. And here is the same exchange that we've gotten used to, right? We start off with hello messages, and we've got 1.254 in this case, and 1.253. And the minute they realize that the 2 of them are present, they start the database description messages on the exchange. And then once they figure out that one might have updated information or more up-to-date information, they start making link state requests of each other. We do the link state updates back and forth. So can I have this? Here you go. And then finally we wind up with the acknowledgments. And in this case, the acknowledgments go right back to the multicast address that is used by OSPF, but sometimes we have direct exchange between the neighboring routers. And then eventually we wind back into the hello messages. Steady state steaming. Now this is just an example of an OSPF routing table. Once we have established our routes, our link state database, right? Once we've completed the synchronization, then we wind up with routing table entries such as this. So we've got some OSPF routes here. There's our admin distance and metric associated with OSPF. Here are some IA routes. So this is OSPF but inter-area. And so this would be an area border router in this case, right? 172.18.0.253. And there we go. So this is a standard routing table entries that you would see for OSPF. Well, there we have it. This video has been the basics of OSPF message exchange and some of the OSPF processes. We talked briefly about the OSPF hello protocol and then synchronization via the database description messages, and then that moves us into the link state requests, advertisements, and then acknowledgments. And after that, we hope that we're all synchronized and we've got a full link state database and a fully populated OSPF routing table. Well, thanks for watching. Thanks for listening. Hey, if you got all the way through this, and if you've done those other OSPF videos, well, heck, that name tag up there is for you. Like and subscribe if I helped, and may those packets always reach their destinations.